Hello and welcome to example sheet 3, question 1. This particular question, we're looking at a Brayton cycle using air as the working fluid. Pressure ratio of 8 is given, so we've pulled that out. Minimum and maximum temperatures of the cycle are 310 and 1160 Kelvin. If we look at this so we know that these are temperatures T1 and T3. And you can see this from drawing the TS diagram. So you're going to have point 1 here, I'm going to pass it up. 1 to the isentropic point at point 2. This is important because the isentropic efficiency is given for the compressor and the turbine, but the actual point is going to be, the entropy is going to slightly increase during that compression to point 2, and of course heat's added Q in from stages 2 to 3. It's really important that you learn these diagrams, and you can draw them quickly in the exam just to visualize, because you can see here point 3 is the highest temperature, point 4 is there. Entropy will decrease in the turbine, but of course, since isentropic efficiency is given, the 0.4s is of interest to us there. Now, this particular question could be solved using the constant CP value assumption. I'm going to do that in the left in blue, or it could be calculated using the variable CP value, which is the tables, and I'm going to do that on the right in green. The reason I'm going to show both on the same thing because the underlying principles are similar, but then there's two techniques. The equations are good because you don't need tables, you don't need the property tables booklet, so you could just do that on the back of an envelope, whereas the tables are useful because they'll give you a more accurate answer. Okay. So first of all, we're interested in the air temperature at the turbine exit. So this is the temperature at 4 that we're interested in. Okay, so from the data sheet, there is this particular equation. N turbine is equal to H3 minus H4 A. The actual point at 4 over H3 minus H4 S, the isentropic point. Okay, so using the constant CP value assumption, we're going to simplify this to CP T3 minus T4A divided by CP over T3 minus T4S. Of course, the CP's cancel. Okay, so looking at the knowns for this equation, we know T3, and we also know the isentropic efficiency of the turbine, but we don't know T4A is what we're trying to find, and in order to do this we need T4S. Okay, so there is another equation given on the data sheet which we can use to find T4S because we've been given the pressure ratio. So it's T4S divided by T3 is equal to P4 over P3 to the power of K minus 1 over K. And of course, K is given on the data sheet as equal to 1.4 when using the standard CP assumptions. Quite simply rearranging this equation, T4S is equal to, of course, subbing in the values, you'll find T4S is equal to 60 bracket times the pressure ratio, which in this case is 1 over 8 because notice it's 4 over 3. I haven't drawn the PV diagram, but if you look at this in the notes when they recommend a textbook, that'll indicate to you why. It's also important that you're aware of the PV diagrams as well as the TS diagrams for each of the cycles. 1.4 minus 1 over 1.4. And that gives you a value of TS equal to 640.7 0.37 Kelvin. Now we found T4S, we can quite simply rearrange the equation for the isentropic efficiency of the turbine, and we can find T4A, which is what's required for part A of the question. T4A is equal to T3 minus N turb bracket T3 minus T4S, which is equal to 733.9 Kelvin. Okay, so looking at part B, we're now interested in the network output. So what I didn't put on the diagram was work in and work out. And of course, the network output is equal to the work out minus the work in. And since the work out is occurring between points 3 and 4 in the turbine, it's equal to H3 minus H4. And the work in is happening during the compressor, it's equal to H2 minus H1. Now, of course, since we're using the standard CP equations, we can change that to CP bracket T3 minus T4 minus CP bracket T2 minus T1. Remember, the CP value is given in the datasheet. It's 1.005 kilojoules per kg Kelvin. Okay, so CP is known, T3 has been given, and T4A we've previously just calculated, and T1 was given. T2A we haven't calculated this yet, so we need to calculate that in order to calculate the network. Looking at the datasheet that's given, you'll see that there's, or you may already know, that there's an equation for the isentropic efficiency of the compressor. And of course, since we're using the constant CP assumption, we can convert this. Of course, we know T1, and we also know T2S, and we know the isentropic efficiency of the compressor. So we can quite easily calculate T2A now by just simply rearranging this and subbing in the values. And that will give you a value of T2A equal to 645.3 Kelvin. Okay, now since we found T2A, we can sub in the values. We have all the values here, and we can quite easily sub them in and find W net. And that gives you a value of 91.25 kilojoules per kg. So that's the answer to part B of the question. Okay, and finally part C is fairly simple, the thermal efficiency. Now we're interested in Q in, since the thermal efficiency is equal to W net, which we previously just calculated in part B, divided by Q in. Now Q in, of course, is equal to H3 minus H2. Now, of course, it can be, since we're using the CP equations, this is equal to, and quite simply subbing these values in, you're going to see what we proved, 1.925 divided by 100.005, 1160 minus 645, 3.3, and this will give you a value of thermal efficiency equal to 17.6%. So I'm going to repeat the question now. I'm going to look at what values we get for parts A, B and C given the variable CP value. So you will be using the Thermodynamics Property Table Booklet. For those of you that are wondering, CP stands for constant pressure specific heat value, and of course in reality this would change at different points within the cycle. The cycle of course is the same cycle here given on the right. First of all, we're interested in finding the air temperature at the exit, so this is T4 actual, so this is this particular point here. In order to find the temperature at T4 actual, we're going to use the same equation from the data sheet for the turbine. Particular equation here. But this time we're not going to use the constant CP value. We are in fact going to calculate the actual values of enthalpy using the Thermodynamics Property Tables Booklet, and as a result, accounting for this variable CP value will give us a more accurate result, and we'll compare at the end to see how far off our equations were. Okay, using table A17, we're able to find the corresponding H3 value. Since we're given a temperature of 1160 Kelvin, the corresponding H value for this is 1230.92 kilojoules per kg, and the pressure ratio PR3 is equal to 207.2. Now we know that PR4 over PR3 is equal to the pressure at 4 over the pressure at 3, which is equal to 1 over 8. Again, refer to the PV diagrams to get your head around this. It's very straightforward once you look at that diagram. PR4 is equal to 1 over 8 times 207.2, which is equal to 25.9. Okay, so looking up a value, the pressure value PR4, 25.9 in the property tables A17, you'll see that you need to interpolate to find that particular value. We are looking at, it lies between this point here and this point here. I'm not going to run through the process of interpolating to find the value in this particular video. If you go back to video 1 of example sheet 2 refrigeration, you will find that the method for interpolation. I'll leave it on the screen here briefly so that you can check if you'd like to check your workings. And when you sub those values into the equations, you'll see that T4S is equal to 680.3 Kelvin. And I'd suggest I've also notice these values here. I've also interpolated while I'm here to find H4S, and that's equal to 692.19 kilojoules per kg. So you'll notice here we are getting slightly different values for T4S compared to when you look over at the other side. Okay, so I've just rubbed out the interpolation just to create a bit more space so I can keep aligned with this. I tried to draw the last method in blue, and I'm trying to draw this method in green using the tables, and I'm trying to keep bits that relate to both methods in black. But you might notice I just did the interpolation in black by mistake, so apologies for that. Okay, so now we have the values for H3 and we have the value for H4S. The isentropic efficiency of the turbine was given in the question, so as a result H4A can be found. We'll give you a value of 789.16 kilojoules per kg for H4A, and you're now just going to interpolate this again using table A17, and that will give you a value of T4A equal to 770.19 0.1 Kelvin. Similar value, about 3 Kelvin, 3.8 Kelvin different using the tables compared to the equations. Notice that the equations are estimating a slightly higher value for the temperature, which will suggest higher efficiency, and we'll look into this later on. Okay, continuing the question using the variable CP value and the tables, of course. Looking at part B, network output. Again, theory is the same. W net is equal to W out minus W in, the work out minus the work in. H3 minus H4 represents work out, and H2 minus H1 represents work in. So scrolling down, you can see this equation here is the same equation we're going to be using. Okay, and as you know, we previously found H3 using table A17, and we also found H4A as well as H1, and of course the pressure ratio corresponding to 0.1 as well is of relevance to us because we need to find H2A, and in order to find this we can then calculate network, which we're looking for. Now of course this same equation over here, you can find that in the data sheet of course. So we know H1, and of course we know the isentropic efficiency of the compressor because that's given. We can find H2S, and then we can find what we're looking for, H2A, put H2A into here, and we found the network. So we know from this equation PR2 over PR1 is equal to P2 over P1. Pressure ratio across 2 and 1 is in fact 8. So then rearranging this, PR2 is equal to 8 times PR1, which is 1.5546, and that gives you a value of 12.44 for the pressure ratio at 2. Okay, so you need to interpolate this to find the corresponding value of H2S at the given pressure ratio. And that will give you a value of H2S equal to 562.58 kilojoules per kg. Then of course you can rearrange this equation here to find H2A. Then once you found H2A, you can sub this back into the first equation we had to find W net. And that will give you a value of 105.3 kilojoules per kg, which of course is significantly higher than what we calculated using the equations. Finally, we're asked to calculate the thermal efficiency of the system, which is equal to the network out divided by Q in. Q in, of course, between points 2 and 3, so hence it's equal to the empathy value at 3 minus the enthalpy value at point 2. So looking here, you can see the same equation, which is highlighted in black, still applies. And it's a fairly straightforward calculation. We know the values for H3 and H2, and we also now know W net because we've just calculated it in the previous question. And that gives you a value of 0.18 and therefore 18%. So you can see that the thermal efficiency is actually higher in reality given variable CP values than it is using the assumption that the CP values don't change. So you can see that the tables give a higher value of efficiency. Thanks.